Okay, so today what we're going to be doing is we're going to be solving a system of equations using substitution. The last video, what we did was we solved it via graphing. Now, graphing is a very simple, albeit sometimes is not necessarily the fastest method to solve a system. This is going to be faster when one of two things happens. When the first thing that happens is when the graph is too large to reasonably graph. And we're going to see a lot of examples like where this has a y-intercept of 74. That's going to be, if we were trying to graph that on graph paper, it's going to be so high up and the slope is going to be so obnoxious that it's not going to be realistic to solve this via graphing. The second time that we're going to use a mathematical method like this is when the numbers don't fall on nice whole digit values. Now what we're going to do today is we're going to solve those nice whole digit values to practice this method, but for future sections, we're going to have things like where x is 1/2, where x is 0.3 repeating. We're going to get weird answers. So let's go ahead and get started. Now, substitution consists of plugging in something. So we're going to solve for one variable at a time. And our 4 steps are you isolate, you plug in, isolate, and repeat. So it's just isolate and plug in are really the only 2 steps. So let's go ahead and see what that means as far as when I'm intercepting these 2 lines. Now you should recognize this is a horizontal line and this is a diagonal line. So when does this horizontal line of y = 2, so if I had a graph and I were to sketch it really roughly, I would have a line something like y is equal to 2. My other line of y = 9x plus 74 is going to intercept way up here, and it's going to continue to go up. So at some point right here, those lines are going to cross, and I want to see where those lines are. So I know it's going to be a negative x and a positive y. Not all the times we're going to be able to tell this by looking at the equations. Right here, we are. So step 1 is isolate. Lo and behold, I already have one that's isolated. Y is equal to 2. So I'm going to go ahead and take that 2, and I'm going to plug it in to the other equation wherever I see a y. And so what I'm going to get is I'm going to get a value of 2 is equal to 9x plus 74. I literally took that value and I plugged it into this equation. And then at this point, we just go ahead and we solve. I subtract 74. Cancel that out. So negative 72 is equal to 9x. I'm going to divide by 9. So I get a negative 8 is equal to x, which is exactly what we predicted. We predicted it was going to be somewhere in this quadrant. So I have a negative 8, solve for the remaining variable, and so repeat for each remaining variable. So I'm going to go isolate, replace. I've already isolated, so I'm going to stick this into one of my original equations to figure out what y is. But wait, don't we already know what y is? Yes, for a horizontal line, we already know one of the values. So we have a solution is at negative 8, comma 2, which is exactly what we predicted. So let's go ahead and try out the next one. Actually, before we do so, some of you might be asking, well, what if I plugged it into this equation? Would I still get a y value of 2? And the answer is yes, because no matter where I plug in the negative 8, I'm going to get the same answer for both those equations. If you got a different answer, we would know something would be wrong. But let's plug it in just to be sure. So if I said y is equal to 9 times negative 8 plus 74, y is equal to negative 72. Yes. So if I plug it into any one of these equations, y is 2 or y is 2. Regardless, my answer is going to be at negative 8, comma 2. So let's try one more, except for this time, instead of with a horizontal line, let's try a vertical line. And so a really rough sketch of what our graph is going to look like is I have x is -3, so I have some line right there, and then I have this thing. So I'm going to draw a quick sketch. My x-intercept is going to be roughly a little over -2. It's going to be somewhere in there. And my y-intercept is going to be somewhere at -13. So I know that it's going to move like this. And so this point right here is going to be where those lines cross. Now, this isn't drawn to scale in any way, shape, or form, but I know that my graphs are going to intercept somewhere with a -x and a +y. Well, we already know that the -x is true because it's -3. We just need to figure out the y. So let's go ahead and plug it in wherever we see an x. So -12. I'm going to plug in a -3. And I'm just going to work the equation. 36 minus 2y is 26. Now also, there's a lawn crew doing work right outside my, my room. So I'm going to do my best to kind of muffle the sound out of this, but please bear with me. I'm going to get rid of the numbers on the same side of my variable. And then I'm going to get rid of the coefficient of my variable. So I get y is equal to +5. And so, yep, -3, +5, we found our solution. Some of you might ask, well, what happens if I plug it into this equation? Does it work the same as up there? Yes, it does. We just have to do a little bit of solving. So let's see if we get the same thing. If I plug in a 5 for my y variable in the other equation. Let's see, that's -12x minus 10. If I add 10 to both sides, I get a, let's go ahead and do this the right way. Cancels out. So -12x equals 36. Divide by -12. So x is equal to -3. Yep. And so this verifies that yes, we do cross at that point. Perfect. And so regardless if you have a horizontal line or a vertical line, we're finding where those two lines meet. And sometimes, again, we'll see the fact that we have really big y-intercepts where the equations themselves might be a little more difficult to figure out where exactly they're going to cross. So I might have, with this one, I have a really high y-intercept with a positive slope, which means it's going to do this. And this one has a really low intercept with a negative slope. So here's where the issue is I could either have the slope cross on the line depending on how I graph this. I could realistically draw it over here. I could draw it over here. Without actually graphing this, I don't know whether it's going to cross above, on, or below. Some of you might say, well, we could use the slopes, and because this is going to be closer to 0, that means it's going to be in the negative range, so it should be right here, and that is true. But again, these have the same slopes, so if I had something of a different slope, it may be impossible to tell. All we know is it's going to cross somewhere on the left. So let's go ahead and figure it out. So if we remember, step 1 was isolate. Step 2 was plug it in. So albeit I don't have something like x equals 3, do I have a value for one of my equations? Yes, we do. So if I told you y was equal to -8, we would plug in -8. Told you y is equal to -75, we'd plug it in. So no matter what I say y is equal to, you plug it in. Well, what if I were to tell you we can plug in more than just a number. What if I said y is equal to negative 8x minus 75? What do? Well, we plug it in. Doesn't matter that we don't have an answer. We're just going to plug it in. So if we have a negative 8x minus 75 that I plugged in equals 8x plus 69, guess what? The only variable I have left is x. I can solve that equation. So let's go ahead and solve it. Plus 8x plus 8x. It's going to get rid of that, which is going to leave me with a negative 75, 16x, 69. We're going to go ahead and subtract the 69. So we have 4, 4, 1. We're going to go ahead and divide by 16. Now this, can't do that off the top of my head, but I can divide them both by 2, which is negative 72 over 8. And I can divide 72 by 8. That's going to give me a negative 9. Perfect. So again, we know that they're going to cross somewhere over here, so I know that the x value is negative 9. What do we do next? We plug it in. So we plug it in part 1, solve, plug it in part 2, and solve. Substitution is literally plug it in and solve, plug it in and solve. Now, here's the joy. It doesn't matter which one you plug it into, because is the blue line going to cross the red line in the same place that the red line is going to cross the blue line? Well, yes. So whichever one looks easier to you to solve mathematically. If you want to plug it in to y equals negative 8, if you want to plug it in there, plug in my negative 9, you're going to get y equals 72 minus 75, negative 3. If I plugged it into the top one. But if I plugged it into the bottom one, we would get the same thing. So if I plugged it into the bottom one, I would get negative 72 plus 69. Y is again equal to negative 3. Again, it doesn't matter which one you plug it into, so you get to make a decision which one looks easier to plug it into. So we know that our solution is at negative 9, comma, negative 3. Boom. And so we know that, yes, we were right. It's going to be this bottom one right there. Perfect. Now, some of you might be asking, well, what if the variable is not isolated? The process is no different. You isolate one of the variables. In this case, I'm going to isolate my already isolated y. We're going to call this substitution part 1. Now, this is going to look a little different, but only in the fact that what we plugged in is in a different orientation. Not that it's solved any different mathematically. We're plugging it in to this part, and we still have to solve for x. The only variable we have left is still going to be our x. Nothing new like that has changed. So let's go ahead and distribute this negative 10, which is going to give us negative 100x plus 40x minus 290 is 950. Next, I'm going to combine my like terms and get negative 60x minus 290. Then I'm going to isolate my x by getting rid of this 290. I'm literally getting rid of that over here, and I have to 290, add it over here. So negative 60x is equal to negative 660. And what that's going to do is that is going to give me an x equals 11. Perfect. And so after I've substituted 1 and found my first variable, I'm literally just going to substitute in for the second one and get the second variable. So let's take a look at how that would work. Do I want to plug it into the top or into the bottom? Again, it doesn't matter. If we plug it into the bottom, y equals -4, and I plug in the 11, I would get y is equal to -44 plus 29. Y is equal to -15. That's going to be the same as if I plugged it into the top equation. -100 times -4, oh, not -4, times 11 minus 10y equals -950, -1100 add my 1100 divide by -10. So it doesn't matter which one we plug it into, so you plug it into whichever one you think is easiest. Regardless, we know we have a solution is at 11, -15. Perfect. And so the next logical step that we could do is we could look at one where, hey, I don't have a variable that's already isolated. It's not a big deal. Really, the only difference is we have to do the dirty work first. So if I have these two values, I'm going to pick one. Looks like it's going to be the easiest to solve for, which means I could either isolate this x, this y, this x, or this y. So I'm going to go for that y. And why do you think? Well, because it has the smallest coefficient. If it has the smallest coefficient, that means that if I'm going to get a fraction, it's going to be one of the most manageable fractions. I'll end up with thirds. I could end up with 12ths. I could end up with fifths. I could end up with 30ths. I want to deal with something that's as easy as possible. So let's go ahead and let's do our first step of isolating that y. So I'm going to say 12x minus 3y. I'm going to get rid of my x. These aren't like terms, so I'm left with -3y is -12x minus 168. And then I have to divide everything by -3. Plus 3 fits into 16, 5 times, 1 left over, 1, 8. 3 fits into 8, 6. So I have this equation. And now, one of the things that people generally assume is they're like, okay, why don't I take this value right here, and we're used to the idea of plugging it into whichever one looks easiest, right? Well, remember, this is the first step, so there is a correct one to plug it into. We do not want to plug it into the second one, because this is the second equation. We have changed how it looks. We have not changed what it is. So if I were to graph these two different equations, they would be the same equation. So when does an equation intercept itself? At all points. We'd get in infinite solutions. So we want to make sure that we realize that my first equation, 30x plus 5y, and my second equation, y is equal to 4x plus 56, is really what we're looking at right here. Top one remained unchanged. We changed how the bottom one looks. So we're going to plug it in to the top equation. I'm going to plug it in to right there, into my y variable. Remember, that's the first step. So this and this are just saying the same thing. So I have 30x plus 5. That's convenient. I have a line already there. I'm going to go ahead and distribute. $30. I'm going to combine my like terms. I'm going to isolate my x. And then I'm going to isolate the variable. So I get x is equal to -9. And so we see the process right here is no different than the process right here. We just had to go through an initial first step of isolating a variable. But these two bricks of work look identical as far as procedure. Plug it in, solve. Plug it in, solve. What do we do after we solve? Plug it into one of the equations, whichever one looks easiest. So after we've solved it, I'm going to plug it into whichever equation looks easiest. So I'm going to plug it into the bottom equation. And just to show you that this is the second one, so we have substitution 1, substitution 2. So y is equal to +20. Now right here, I could have plugged it into the other equation. I would have gotten the same thing. Just to show you, 30 times -9 plus 5y is -170. y is equal to 100. I divide both sides by 5. I get, again, y is equal to +20. So I know that no matter what, I have a solution is at -9, +20. Oh. And so even if they're convoluted, the idea is we just got to go through and solve for one, plug it in, solve, plug it in, solve. Literally all substitution, plug it in, solve, plug it in, solve. The last one, this one's just to figure out how to deal with fractions. Fractions are no more difficult than anything else. Plug in your value. You solve. Now, typically the way that I handle this is I'm going to handle this by saying, hey, I want to get rid of these two fractions. And the way that I do that is I'm going to go ahead and distribute a 7. Why would I do that? Well, how do I get rid of divide by 7? Times 7. And when I distribute this to everything in the equation, this cancels out. So I have a -4x. And it doesn't cancel out on these three, so I'm going to multiply each of these three terms by 7. So 7 by 7 is 49. -3 times 7 is -21. And 23 times 7, well, it's 1, 2, 14, 16. It's 161 over 4. So I got rid of one fraction, and then I just do it again. So for this time, I'm going to get rid of these fourths by multiplying everything by 4. These two cancel out, these don't, so I'm going to multiply both of those by 4. Boom. And then we solve, just like we've always done. I'm going to combine my x's. Going to get rid of the other term. and then I'm going to isolate the variable by getting rid of the coefficient. So plugged it in. So substitution number 1, or I guess the other way around. Substitution number 1, substitution number 2. So it doesn't matter again, whichever one I plug it into. I plug it into the top one. These cancel out. Y is equal to 4 plus 7. Y is equal to 11. Or if I plug it into the bottom one, so I'm going to multiply these. I get a 21 over 4 plus 23 over 4. Y is equal to 21 plus 23 is 44 for 4. So y is equal to a positive 11. Again, it doesn't matter which one you plug it into. I know I have a solution. Negative 7. Can't really tell that's two different things. I have a negative 7, comma, 11. And there we go. So today what we're doing is we're doing a more advanced set of substitution. And really all this is we're dealing with more realistic values, which are fractions and decimals. And we're going to see that the process is no different than what we've done prior. It's just we're going to have to do a lot of clearing of fractions if we're uncomfortable with working with fractions on a general basis. And normally I would recommend clearing of the fractions because it makes the math a lot simpler to do by hand. However, if you have a calculator or a spreadsheet, it's probably going to be the easiest way to do it. Also, we'll learn about a process later on called elimination, which will make your life much easier. But for today, let's go ahead and get started. So, as we always remember, when in substitution, if I have a variable that's isolated, I'm going to take what y equals, and I'm going to plug it in, and I'm going to replace my other variable y with what y is equivalent to. And so what that's going to do is that's going to give me a negative 22 over 13x minus 107 over 13. And so what I've done is I've literally replaced my y with what y equals, with its value. Now I don't care that its value contains a variable, an unknown sample. I just know that that's what y is. If y was 2, I'd plug in 2. But in this case, y is negative 22 13ths x minus 107 13ths. I literally rewrote this equation, but I filled in the value for y. The next thing that we're going to do is we're going to get rid of some of these fractions. And now if I were to simply look at this fraction and say, okay, that's negative 5 divided by 11. How do I undo division? Well, multiplication. So let's go ahead and let's undo division with multiplication. I'm going to multiply everything in this equation by an 11, which means that these two are going to completely cancel out. Multiply and divide by 11. Over here, however, they're not. I'm actually going to have to multiply the top half of them by an 11. So let's see what we get. So what we get with the negative 22, that becomes a negative 242. That becomes a 1177. So we see these two 11s cancel out, and both these got multiplied by a factor of 11. And the next thing, if you want to get rid of the other fraction, let's go ahead and multiply it again by a 13. It's going to cancel out these two, and it's going to stay on those, which leaves me with a negative 242x, 1177, equals negative 65x minus 1885. Perfect. And now we have what looks like a single variable three-step equation. Our first step is going to be, let's go ahead and add a 242x to both sides. Actually, I'm going to go ahead and draw my line right here, so that way I separate left and right. It's going to cancel that out over here. Negative 1177 is equal to 177x minus 1885. I'm going to add that to get rid of it over here on the right. It's going to leave me with a 177x. That's going to be 708. My last step, I'm going to get an x is equal to 4. Perfect. So once you've isolated, this has already been done, you plug it in and you simplify. When you finally get your answer, what you do is you plug it into one of your original equations. So I'm going to plug it in to the bottom one simply because that looks like that might be a little easier. I may be mistaken, but it's all about looks. So I plug it in. Now we could clear this fraction just like we did over here, but what we notice is they're both over an 11. So what we end up with is a negative 20 minus 145, and because they're both over 11, we can plug them both over the same denominator. So in this case, y is equal to negative 15, which means we have a solution. Let's do this in orange. So our solution is at 4, negative 15. Perfect. And so we notice that the process isn't any different than what we've been doing. So let's try one that's in a slightly different format. This one is not in slope-intercept form, but one of the things that we do notice is that most of us are probably going to go and try and isolate that 2y, simply because it's a nice whole number, it doesn't have a fraction that we're going to have to deal with, and it's a positive coefficient, unlike this where it's negative. So that's going to be our most likely bet if we're using the substitution method. So negative 38 over 3x plus 2y is 136 over 3. And so what we would do to isolate that y is to start, I would add 38 over 3x. Which means that goes away. And then I get a 2y is equal to 38 over 3x plus 136 over 3. And then now I'd be tempted to continue on and divide everything by 2, but I'm going to take a really quick pause and say, hey, what do I see? Well, I see what 2y is equal to. And I know I need in my other equation to plug in a value for 2y. So why don't, instead of continuing to solve this, instead of dividing by 2, plugging it in and multiplying by 2, why don't I just plug in this value right here? Because I know what 2y is. That's asking for a 2y. So I would say, okay, 3/4 x minus 38 over 3x plus 136 over 3. I would plug that in to this equation right there. And I would get this. 3/4 x minus my value for 2y equals negative 43 halves. So let's see what we get. Okay, so far we're off to a good start, but I have 3 different fractions. Now what we could do is I could do like what I did right here, and I could multiply by an 11, get rid of one of them, then multiply by a 13 and get rid of the other one. But why don't we just speed things up a bit? If I want to get rid of a divide by 4, I multiply by 4. if I want to get rid of a divide by 3, I multiply by 3. And if I want to get rid of a divide by 2, well, the 4 would already cover that. So if I look at this, I could say, why don't I just distribute a 12? And that will get rid of everything. So 12 divided by 4 is 3. I'm going to multiply the top of that by 3. If I multiply this by 12 and divide by 3, 12 divided by 3 is 4. I would do the same thing right here, multiply by 4, and then because 12 divided by 2 is 6, I'm actually going to multiply that by 6. So what we end up with is 3 times 3 is 9, and then we have 4 times 38, which is going to be negative 152. Then 4 times 36 is negative 544. Then we get negative 258. So far, so good. Now at this step, it's just as simple as solving for a variable. Isolate the variable or isolate the term. And then once you've isolated the term, go ahead and isolate the variable. Boom. I get an x equals negative 2. And now once we solve for that variable, most of the time we're going to go plug it back into the original two equations, but we could also plug it into our newly modified equation. And so really we're just gonna have to look and say, okay, is the top one or the new top one or the second one easier to plug it into? Long story short, none of them are really any easier than the other. So I'm just gonna go ahead and plug it into the second one. So 3/4 negative 2 plus 2y is negative 43 over 2. So what I get here is a negative 6/4 is 2y, negative 43 over 2. I can use the same trick here as here to get rid of all three of these fractions. Now, if I divide by 4 and multiply by 4, they're going to cancel out. So nothing goes there. Nothing cancels out here, so everything gets multiplied by 4. And then 4 divided by 2 is 2. What that gives me is a negative 6 minus 8y is negative 86. Go through solving for your variable. Get rid of the coefficient by division. So we get y is equal to 10, which means we have a solution at negative 2, 10. And so we see with fractions, nothing really different. Isolate and plug it in, like with number 1, solve it, plug it in again, solve it. With step 3, isolate and plug it in, solve it, plug it in, solve it. Substitution is a very simple process, even when they're complicated scenarios like this. The reason why we push it is because this is how a computer program works. You must define your variable, and once your variable is defined, the computer does not care how many steps it takes to get to the answer. It will find you what the answer is. And then it'll take that answer and do something else with it. This is what we call a loop until function, and you're going to see a lot about them if you take any sort of computer programming class. So, now that we've covered fractions, let's cover a few with decimals. Nothing too terribly crazy about these. These are going to work pretty standard. When we have two equations like this, where I already have a y value that's isolated, I'm going to go ahead and I'm just going to plug it straight in and see what I get. So plug in my value for y. And then basically, we solve. That's it. Nothing too complicated about it. Now, you may be uncomfortable with solving equations like this where we have decimals. Remember, if you don't like the decimals, how do you move a decimal place? What do you multiply by? Just multiply by 10, which moves the decimal 2 places for each time you see it. So that's a negative 425x plus 150. It's negative 325x plus 350. So we see all we did was we moved the decimals 2 places for each one of those. Because I didn't multiply by 10, I multiplied by 100. When we're right here, I'm just going to go ahead and I'm going to add 425x. 425x. I'm combining my x terms. I'm isolating my x term. And then I'm isolating the coefficient. Boom. Once I've isolated it, I plug it in. .25, 2, plus 3.5. Now again, I could get rid of these decimals just like we did over here, but because these are nice rounded numbers, I'm just going to go ahead and work with it. Negative 6.5 plus 3.5. Boom. So we have a solution at negative 2, comma negative 3. Awesome. And so now that you've seen how to work decimals, go ahead, pause the video on number 7, see if you can't work it out, and then come back and watch to see our explanation. Okay. Go ahead and take a look. Now again, most of you probably go for the smallest variable, which means that negative 4.4x. We're going to have to do a couple things to it. And then at this point, when I want to divide by 1.1, that scares a lot of people. As of right now, I just moved a term. So one of the big things, to get rid of a single decimal place, multiply by a factor of 10. That's going to move everything over by 1. And so then you can go ahead and you can divide in peace. And say y is equal to negative 4x plus 2. And so remember, we're going to plug that into the other equation. But because this equation and this equation are the same thing, I'm going to have to plug it into the lower equation. Okay. And again, if you're uncomfortable distributing or doing anything with decimals, just go ahead and get rid of them. Move the decimal over by multiplying everything by 10. Now, what a lot of you are probably asking is, wait, hold on. If I multiply everything by 10, why didn't I change what was in blue? Now, remember, these are for the most part a set of parentheses. If I would multiply a 4.1y times 10, that'd become a 41y. It wouldn't become a 4110y. That would be double distribution. We want to avoid that. So that would be exactly what's going on here. If I had a 4110y, I'd be double distributing. And we cannot, under any circumstances, do that. Sorry, 41 times 12. That is definitely not 42. 41 times 12, or 41 times 2, because somehow my 2 turned into a 12. Go ahead and cancel that out. It's just 41 times 2. That's going to become an 82. There we go. And so now it's just solving an equation. Combine my x's. So I get a negative 410x plus 82. Isolate the x term, get rid of this. And then isolate the variable by getting rid of the coefficient. So I get x is equal to negative 2. And then normally what I would do is I would come all the way up here and I'd plug it into one of these, but don't forget, my top equation is this new equation. So I can stop and say, hey, does that one look easier? For most of you, you're gonna say, yes, that looks a heck of a lot easier than this one. So let's go ahead and plug it in right here. Negative 4, I'm plugging in negative 2 plus 2. So we say, hey, found the solution. Is that negative 2, comma 10. Boom. That is how we do advanced substitution. So today what we're doing is we're doing an accelerated form of substitution, and this is what we're going to call elimination. Now, elimination has a few different requirements before we jump into it. The first requirement is that all terms are listed in the same order for both equations. What we notice is we have x, y on the left-hand side, and then we have our constants on the right. And for today, we're going to do every equation is going to be set up in this. They're all in standard form. Now, is that typical? Sometimes not, but it is necessary to use this accelerated version, and it's necessary for elimination. The second requirement to successfully execute elimination is that the equations have to be modified so at least one variable will cancel out with the counterpart of the other variable. What that means is that I have a positive 1 and a negative 1. These cancel each other out. I don't care about the 7 and the 3 because I only need one variable to do that. Over here we have a 4x and a negative 4x. These will cancel out. I don't need both of them, just as long as one of them. If on the chance, as we're going to see, they don't cancel out, we're going to figure out how to modify the equations so that they do. And I think it's best to start off with showing you why this is an accelerated form of substitution. Now, I'm going to use number 1 as an example, and I'm going to solve it using the old method of substitution so that we can see how elimination works. So with substitution, normally what you do is you'd pick one of these variables, probably this top y, and isolate it. So I would say, okay, so 7x plus y is equal to 8. I would subtract my 7x, cancel it out, and I would have y equals negative 7x plus 8. Then what you would probably do is you'd say, okay, I'm going to take the y from my top equation and plug it into my lower equation. So I would say, okay, let's plug that into 3x minus y is equal to 2. So now that y is 3x minus Negative 7x plus 8 equals 2. And I'd solve for x. So I distribute this negative, 3x plus 7x minus 8 is equal to 2. And then here's where I'm going to show you the example of what's going on. If I add the 8, I would have a 3x plus 7x on the left, and I would have an 8 plus 2 on the right. So pause real quick and take a look at your original equation. Think, where do I see a 3x and a 7x on the left, and then an 8 and a 2 on the right? So where do I see that on the left and that on the right? Well, that would be our original two equations. What we notice is the fact that my 7x and my 3x are on the left. So why don't I just take 7 and add it to 3 and get a 10x on the left? Why don't I take my 8 and my 2 on the right and add that up to give me a 10? And then what do we notice is not here in this equation because we substituted it away. We do not have a y value. And so this shortcut involves skipping this isolation and plugging in of the first variable. And it says if the coefficients cancel out, add the two equations as they are, and solve for the remaining. So we have skipped several steps right here. Divide by 10, divide by 10. And what we have is x is equal to 1. Look at that. 2 steps to solve. This was 1, 2, 3, 4, 5, and more steps, because there would have been a 6th and a 7th to combine terms and then isolate the x. So we literally saved ourselves 5 steps worth of work. But is elimination actually anything different? No, it's just an advanced form of substitution. So when you ask, why don't we learn this before substitution? Well, this is substitution. So every math teacher is going to show you substitution beforehand because it's a necessary part of what's going on. We're not going to teach you how to build an engine before we teach you how gasoline works. So we're going to give you the gas, and now we're saying, hey, build your engine. Take that x equals 1, plug it into the equation of your choosing. So 7 plus y equals 8. I'm going to plug that into the top equation. That's going to give me a 7 plus y is equal to 8. I'm going to subtract my 7. Cancels out. So now I have a y is equal to 1 as well. So now the solution is at 1, 1. The point where these two lines cross is at 1, 1. So pretty exciting. That saved us a lot of time from what we've done previously. Let's try it one more time. What I notice here is that my x's are going to cancel out. So if I do it the old-fashioned way, let's try and eliminate the x's by substituting in a value for x. So let's start with the top one. So if I had a 4x plus 2y is equal to 6, first I'd get rid of my 2y. Go away. So I have a 4x equals negative 2y plus 6. And then I would divide everything by 4. Now I'm going to leave it in unreduced form like this, simply because I know what's about to happen. I'm going to take this and I'm going to plug it into that bottom equation of negative 4x plus y is equal to negative 15. So it's negative 4. Here's my x, negative 2/4 y plus 6/4 equals negative 15. And this is why I left it in non-reduced form, because I knew that these 4's are going to cancel out, and I'll have 2y minus 6. Oh, I forgot my plus y. Plus y is equal to negative 15. Now if I move that 6 over, what's going to happen is I have 2y plus y on the left, and I have 6 minus 15 on the right. And what I notice is that exactly as I've set up right here, my x's are going to cancel out. 2y and y is going to give me a 3y. 2y and y is going to give me a 3y equals exactly where my equals is. 6 minus 15 is going to give me a negative 9. 6 minus 15 is going to give me a negative 9. So again, elimination is not anything different. It's just skipping a lot of this middle work. So 3x equals 9, divide each side by 3, and I get y is equal to negative 3. That's a lot less work than what's over there. Plug in my y of 3, I'm going to plug it into the bottom one. So negative 4x plus negative 3 is equal to negative 15. What I'm going to do is add my 3 to get rid of that. Negative 4x equals negative 12. Then I'm going to divide by my negative 4. And I get x is equal to positive 3. So now these two lines cross and have a solution at 3, negative 3. Boom. So pretty gnarly stuff. We save a lot of work by knowing the fact that if I were to substitute out the x's, I would just be left with what's left in the two equations. So now what we see right here is my two y's or my two x's aren't going to immediately cancel out. But one of the conditions is that the equations can be modified so that the variables will cancel out. And so one of the ways that we modify variables is I'm going to take one of the equations, and in this case, I'm just going to change the sign on that y, which means I'm going to multiply everything in that top equation by a negative 1. So I have negative x minus y positive 3. The bottom one I'm going to keep exactly the same. So that when I add them together, guess what happens? Those go away. 3x, negative 15. Divide by 3, x equals negative 5. Perfect. Now I'm going to take that negative 5 and I'm going to plug it into whichever equation I think works best. I'm going to plug it into the top one. So I have a negative 5 plus 3, or not plus 3, plus y is equal to negative 3. I'm going to add 5, those cancel out. Y is equal to 2. Pretty quick stuff. So I have a solution is at negative 5, comma 2. Perfect. Now, how about you try one? Go ahead and try out number 7. What we notice is that my x's look pretty dang close to canceling out. I would just need to change the sign. So go ahead and pause the video, see if you can't solve this, and then we'll catch up. Okay. So what I'm going to do is I'm going to modify this top equation by multiplying it times a negative 1. It's just going to change all these signs. I want a positive 10x, a negative y, and, well, 0 doesn't have a sign, so it's going to stay 0. The bottom one is going to stay exactly the same. So when I combine them, my x's disappear. 2 minus 1 is 1. Hey, I've already got my first answer. And if I plug that in to that equation right there, I get 10x plus 0 equals 0. So that's going to be negative 10x equals 0. If I divide both sides by 10, what we get is we get x is still equal to 0. So I have a solution 0, comma 0. Perfect. And now this modification of the equations, that can go any direction. We notice right here I have a 10 and 18. Changing the signs isn't going to fix that. The 2 and 3 are already opposite signs, but a 2 and a 3 don't cancel out. So if I can multiply the equations and make them bigger, why don't I just go ahead and figure out what can I multiply 10 and 18 by to get a number that they both will be valued at and cancel each other out. That would be the least common multiple. In that case, it would be 90. And in this case, it would be 6. Let's go with the 6. That seems like a lot more reasonable of a number. So what do I multiply 2 by to get 6? Well, 3. What do I multiply 3 by to get 6? Well, 2. So let's see where these new equations take us. Multiply everything by 3. Multiply everything by 2. Oh, perfect. When I add these two equations together, it goes away. So let's go ahead and divide by 66. So we get x equals 2. Perfect. Let's take that x and I'm going to plug it into the top one. So 10 times 2, I know it's an x. And I'm going to solve. So that gives me 20 plus 2y is 26. I'm going to subtract my 20. 2y is 6. I'm going to divide by 2. And so I get y is equal to 3. And so my solution for this last one is at 2, 3. And there we go. So today we're going to be solving systems of equations with elimination that are a little more complex than what we've seen before. And so let's start out with kind of where we left off last time. And we have two equations where the variables are lined up. I have x, then y on the left, and I have my constants on the right. So I don't need to worry about reorganizing the equation. I just need to worry about finding the least common multiple between either 3 and 64, or the least common multiple between 3 and 8. Well, most of us are going to go for the least common multiple between 3 and 8 because that's a 24. I know that the least common multiple between 3 and 64 is going to be 192. Yeah, we're going to go for the 24. So what do I multiply 3 by to get 24? I'm going to go ahead and I'm going to multiply it. And I'm going to do this in green. 3 times 8 is going to give me 24. And on the second equation, I'm going to multiply 8 times 3 to get me 24. The signs are already opposite, so I don't need to worry about making one of these negative. I'm just going to multiply by an 8 and a 3. And so my top equation is going to give me a 24x minus 24y equals, let's see, 36 times 8 is going to give us 288. 64 times 3 is going to give us 192x plus 24y is equal to, let's see, 48 times 3 is going to give us 144. Boom. And so now what we look at is when we go ahead and we combine these, our y's are going to cancel out. And we're going to be left with, let's see, this is 216x equals, let's see, that's going to give us a 2, 3, 4, negative 432. And then in this case, we're just going to go ahead and solve this by dividing by 216. And we get x equals negative 2. There's our first answer. And we know that once we get our first answer, we're going to go ahead and plug it into one of these. I'm going to plug it into the top one because those look like smaller numbers. And we're going to see what we get. So we get 3 minus 3y equals negative 36. And I'm going to plug in a negative 2 for my x. 6 minus 3y. We're going to go ahead and we're going to add our 6. And then we're going to divide by -3, which is going to go ahead and give us y is equal to a positive 10. So we know that we have a solution, -2, 10. Perfect. And so these two lines cross at the point -2, 10. So, and then one of the common things that we see is that the equations don't need to be in standard form. We've only seen standard form up until this point, but with this, the variables are in the same order. I have y on the left, and I have an x, then a number on the right. It doesn't matter that it's not in standard form where we have x, then y equals a number. You can have them in whatever form you want. It does not matter. So we're going to look for the least common multiple between either 2 and 8, which is going to be 8, or between 64 and 10, which, to the best of my knowledge, is going to be, I believe, 320. We're going to go with the 8. So I actually don't need to modify the top equation at all. It's already at a -8. So what I want to do is I want to somehow multiply this bottom equation to get a positive 8. Well, 2 times what gives me, -2 times what gives me positive 8? Well, -4. So I'm not going to touch the top equation. I'm going to multiply everything on the bottom equation by -4. So I get a positive 8y, I get a positive 40x, and I get a positive 160. And now when I combine these, my y's cancel out. Now I want you to be careful here because we notice that the y's cancel out. Oftentimes students will move the equal sign so that when we combine these and we get a -24x and we get a -24, they'll move the equal sign in between the x and the number. Remember, both the x and the constant are still on the right-hand side of the equation, so the equal sign remains right here. There is a 0 over there. Don't forget about the hidden 0. That's a very common mistake that a lot of students make. Just make sure that it's not one of us that does that. Once we do that, we go through the process of isolating the variable. 24x is positive 24. We divide by -24. We get -1 is equal to x. Cool. And then we take that, we can plug that into whatever equation we want. I'm going to plug it into, in this case, the bottom equation. So -2y equals -10 times -1 minus 40. So -2y is 10 minus 40. 2y is -30. And divide by -2. Y is 15. And so we have a solution, a point where the lines cross at -1, 15. Perfect. And so we notice now that the equations, it doesn't matter what order they're in as long as they are in the same order. But what happens if, for instance, they are not in the same order? Well, all we need to do is rearrange the equations a little bit. And it doesn't matter which order you put them in, but let's go ahead and take a look. Now I have an equation, x, y equals a number. This is an x equals a number y. So what I want it to be in is I want it to be an x, y equals a number. I'm going to put it in the form of the top equation, which means I need to relocate that 5y. And so I'm going to copy down the top equation, -4x plus 4y is -72. And I'm going to move that 5y across so it will become a -5y. The 20x hasn't moved, it stays positive. The 165 hasn't moved, it stays positive. But because the 5, I changed it to the other side, it changes signs. And this allows us to either look at least common multiple of 20 or the least common multiple of 20. Well, I'm going to go with the x's simply because that's already a 20. I know I don't need to do anything fancy to the bottom one. It's positive 20. I need this to be a negative 20, which means I multiply the entire equation by 5. So negative 20x plus 20y is, let's see, 72 times 5 is going to give us 360. And now when we add these together, my x's conveniently cancel out. We have 15y is equal to, let's see, 360. That's going to be 200. It's going to be negative 195 if I did my math correctly. Let's double check. Let's see, 360 minus 165. Yes, negative 195. And then we're going to take that and we're going to divide it by 15, which is going to be 13. So y is equal to negative 13. And we're just going to take that and plug that into either equation. We're going to plug it into this bottom one. Because the x is already partially isolated, it means that I might have to do a little less work. 65 plus 5 times negative 13. 20x and then at this stage we divide by 20. We get x is equal to 5. And so we find out that the solution to our system is at 5, negative 13. There we go. And so now that you've seen what happens when we have to reorganize the patterns, I want you guys to take a pause, look at number 7, see if you can't do it yourself, and then resume the video to see how you did. Okay, so let's take a look. I have y equals x minus 136 and x equals y minus 238. I'm going to go ahead and I'm going to resume the default x, y equals a number, which means I'm going to move this x to the left and that y to the left. I'm going to rewrite my two equations. Negative 4y. Well, apparently I'm rewriting this in y comma x. So let's turn that into a y and let's turn that into an x simply because I've already written the 4y. My positive 16x becomes negative 16x. That stays the same because it didn't move. I move that over so that becomes a negative 7y. 28x doesn't change, neither does the 238. And so now we're going to look at either the least common multiple of 28, or we're going to look at the least common multiple of, let's see, that's probably going to be 80. I'm not 100% certain. Let's see, 80 divided by 28. Nope. Okay. So this one's most likely going to be 16 times 28 divided by 4. This one's going to be 112. Just because that took so long to figure out what the least common multiple was, let's go ahead and go with the 28. It's a little easier to figure out. And now, some of you might be looking and saying, oh, hey, I noticed that all 4 of these are divisible by 4, or all 3 of these are divisible by 7. Can I instead not go for a positive? Can I reduce these to make my numbers a little easier? And yes, you can. So I'm going to work it this way first, and then I'm going to show you a shorter way by reducing the problem. So this is going to give me, oh, sorry, I need to get times 7 and times -4. So if I multiply that by 7, I get -28y. 16 times 7 is going to give me 112. And then 136 times 7 is going to give me 952. This is going to give me a positive 28y. 28 times 4 is going to give me a positive 112. And then 238 times 4 is going to give me a positive 952. Some of you might notice that all of these terms cancel out, and I'm left with the fact that 0 equals 0, which means these are the same line. And so if these are the same line, how many times does the line touch itself? Infinitely many. And there we go. And for those of you who are thinking about, could I solve this by reducing? Well, yes. What happens if instead I divide by 4 and I divide by 7? Could I do that? Well, yeah. If I divided this by 4, I'd get a negative y minus 4x equals negative, let's see, 136 divided by 4 is going to give me 34. Divide by 7, negative y minus 4x equals negative 34. We notice that again, these are the same line, which in both cases means that there are infinitely many solutions. And there we go.